The way that we found a confidence interval for a single mean in Chapter 3 is similar to the way that we found a confidence interval for a single proportion. You can generate the bootstrap distribution based on the sample data, and from there, either you can use the estimate of the standard error in the upper right corner of the picture to find a 95% confidence interval, or you can use percentiles. The central limit theorem will apply here as well, just like it did for single proportions. So as the sample size increases, the sampling distribution of the sample mean will get closer and closer to a normal distribution. Consequently, if you have a large enough sample size, the distribution of the sample statistic will be approximately normal. This sequence of pictures is supposed to illustrate that idea. If you look at the population in the upper left, that's clearly right skewed. And then we have three sampling distributions. The one where the samples are of size 8 still looks right skewed, looking at it just based on where the peak is. The one where n equals 20 in the lower left, that looks better, although still a little bit right skewed. And then n equals 32 looks pretty good in the lower right. So it looks like here 32 is big enough, but 8 and 20 probably aren't. Unlike with a single proportion, there isn't a fixed cutoff. And even with a single proportion, you can argue that it's not fixed, but it is based on whatever p is, because you just need n times p and n times 1 minus p to both be at least 10. There isn't a rule like that here. Generally, if you have a really crazy looking initial distribution, you're going to need something kind of big. And if you're starting off with something that's almost symmetric to begin with, you probably don't need a very big sample size. For most initial distributions, 30 is going to be big enough. That's how our book handles it. Our book just says as long as n is at least 30, that's large enough. So that's how we'll handle it here, just like it says in blue at the very end. When the sample size is at least 30, we'll be able to approximate the sampling distribution using a normal distribution with a mean of mu and a standard deviation of sigma over the square root of n. Watch out for that standard deviation of the sampling distribution. It's really easy to forget that square root of n if you're not used to doing this. That's a very common mistake here, so watch out for that. These two pictures, just like how there were pictures like this with a single proportion, are supposed to illustrate that this actually does work. The graph on the right looks like a smoothed out version of the one on the left, and that's the point of having these pictures in here. In theory, that formula that's toward the top of the screen would be how you would find a confidence interval for mu. But in reality, that doesn't work. The reason that doesn't work is that it involves a sigma. And in order to have a value for sigma, the population standard deviation, you would have to have mu. Because by definition, the standard deviation is the average distance from the mean. So you'd have to know what the mean was in order to compute the standard deviation. So therefore, you would need to know what mu was in order to get sigma. That's a problem, because if we're trying to estimate mu, presumably we don't know what it is. That means that we're not going to have sigma. So we're going to have to use a point estimate for sigma, and the point estimate that we're going to use is s. This is sort of like with a single proportion, we had this kind of thing where underneath the radical, you don't know what p is, so you have to use a p hat. We have to do a similar thing here where there is an obvious point estimate, but that's actually going to cause another change here. Because when you use s instead of sigma, in the formula, that's going to introduce a decent amount of additional variability. So there has to be another adjustment there to account for that variability, and that's to change the critical value. So we're going to need something a little bit bigger, and in order to do that, what we're going to do is we're going to have to use a distribution that has thicker tails. And the distribution that will work for this is something called student's t-distribution. First of all, the reason it has that awkward name is because the man who developed it did not have the permission of his employer to publish under his own name, so student is his pseudonym. That's why that nomenclature looks so awkward. Most people just call it a t-distribution. That's what I usually call it, but its full name is student's t-distribution. These are the properties of student's t-distribution. It is bell-shaped, so it does superficially look like a normal distribution. More specifically, it looks like a standard normal since it's centered at 0. It's characterized by something called the degrees of freedom, which is something that hasn't come up yet. Essentially, the idea is that the t-distribution is adjustable. Based on the degrees of freedom, that'll adjust how thick the tails are and therefore how tall the peak is in the center. The area under the curve always has to be 1, so if the tails get thinner, then the peak has to get taller to preserve the area under the curve equals 1 idea. Right now, the degrees of freedom won't be anything overly complex. It's just n minus 1, where n is the sample size. For a single mean, that's all it is. It'll get a little bit more complicated later, but for right now, that's it. If the degrees of freedom is a relatively small value, then that's a small sample size, so you're going to have a lot of extra variability to deal with, so you need big, thick tails. But if the tails are thick, then the peak has to be kind of short, because the area under the curve has to be 1. But then if you have a larger value for the degrees of freedom, that's a bigger sample size, less variability, so the tails can be thinner, but if the tails are thinner, then the peak has to be taller to compensate for that, to keep the area under the curve being 1. And then the last part, the limit as n approaches infinity of the t-distribution would be a standard normal. That's true, and I wouldn't advocate using a t-table for anything really in this course, but with a printed table you can actually see this, because any printed table of a t-distribution, the last line, the last row, would be for infinite degrees of freedom, and there you see those values from a standard normal. You see the 1.645 and the 1.96 and the 2.576. They're all in there. This picture is supposed to illustrate the idea of the smaller degrees of freedom having thicker tails and a lower peak, and you can see it right here. That red curve, the peak is certainly a lot shorter than the blue peak, and the tails are thicker. And that's the one that has the smaller value for the degrees of freedom. I guess you could look at that from the opposite perspective as well and say, well, the blue one, there the degrees of freedom is higher, so the tails are thinner and the peak is taller. That would also be true. That's the opposite perspective of the same thing. This picture is also there to illustrate that really soft purple, where it looks more like a hump than a bell curve. Not only would that be for n smaller than 30, that would be for when n is really small. I would say 5 or less to get a shape that looks that weird. But the idea is that as n gets bigger, then the peak is going to get taller and the tails are going to get thinner. That's really all that picture is supposed to be signifying. There's the formula that we would actually use to compute a confidence interval for mu. The t star is the critical value, and the t signifies that it comes from a t-distribution instead of a standard normal. And to make sure inference is appropriate, if n is at least 30, we can apply the central limit theorem, and we're all set. That's the easy scenario. The other one, if n is not large enough, if n is less than 30, check the sample to make sure the underlying distribution appears to be normal. The best you can do here from looking at the sample is you want to see something that looks kind of normal. So what you want to see in that histogram is that you want it to be symmetric with a single peak and no outliers. The symmetry doesn't have to be absolutely perfect, but you don't want it to be something that's clearly skewed. In this example, we've got all of our sample data in the second bullet point. Got the sample mean, sample standard deviation, sample size in there, and we want to find a 95% confidence interval for the mean number of days that the company's vehicles are out of operation. First thing is, can we apply the central limit theorem? Yes, because n is 75, which is greater than or equal to 30, so we're all set there. We don't have to look at a histogram of the sample. We've got a big enough sample size to apply the central limit theorem, so it's the easier scenario this time. Since the sample size was 75, we need to use a t-distribution with 74 degrees of freedom to find the critical value, and that's what we have here. If you look toward the right side of the screen, my degrees of freedom is 74. I have two tails selected in the upper left, and I'm specifying 0.95 in the center, and my critical value works out to be 1.993, which is a little bit bigger than what you would have from a standard normal. From a standard normal, you'd have 1.96, and generally that's what happens, that the critical value that you get from a t-distribution will be a little bit bigger than the one for the same confidence level that you would get from a standard normal. There's the computation for the confidence interval. First, substituting everything in, we already knew what x bar, s, and n were, and we just got t star, the critical value. Substituting all those in and simplifying, I rounded off the margin of error to 3 places. Since x bar and s went to 2, the general convention is to go at least 1 place farther than the original data, and those would be what the original data consists of here. And what we ended up with is the interval from 14.818 to 17.022. And then the interpretation, so 95% confident at the beginning, endpoints at the end, and the parameter in the middle, it's a mean, The population is all the company's vehicles, and the specification is the number of days out of operation. So what's there? We're 95% confident that the mean number of days out of operation for all the company's vehicles is between 14.818 and 17.022. I think that's about as short as you can get that while still getting everything in. And if you look at that interpretation, it's the exact same type of thing that we would have done in Chapter 3. Nothing changes there. It works exactly the same way. The only thing that's different from Chapter 3 is the way that we're getting a margin of error. The stuff with the t-distribution and these computations, that's new, but what the interval ultimately gives you, which would show up in the interpretation, it's exactly the same. Computing a desired sample size. There's one thing that might look wrong right away. Considering all that talk about the t-distribution, why is there a z-star and not a t-star? It seems like there should be a t-star, since that's what we were just doing with the confidence interval. The reason that there's no t-star is because in order to use a t-distribution, you would need a value for the degrees of freedom, which is computed as n minus 1. So you'd have to know n, the sample size, already. But if you're solving for the sample size, you don't know what it is. So using the t-distribution effectively becomes impossible here. That's why it's a z-star and not a t-star. We're forced to use the standard normal as kind of a point estimate because we don't need the sample size for that. All we need is the confidence level. So ME is the bound on the margin of error, Z star is the critical value from a standard normal distribution, and then sigma tilde is an estimate of the population standard deviation. There are a couple of estimates for the sigma tilde. I have 3 options written there, and the book talks about the first 2 as being separate things, so I kind of played along in writing this out. But I view the second one as a special case of the first. So what I think is important here is really the first bullet point and the third one. Either you have an estimate that you can use for the standard deviation, you have an S, a sample standard deviation of some kind that's relevant, and then you can use that. That would be the first bullet point. Or you have nothing, which is the third one, where then you have to estimate the range, so you estimate the maximum and minimum values, take the difference, and there's your range, and then you divide that by 4, and that's your sigma tilde. That usually overestimates by quite a bit, but that's okay. That's going to give you a sample size that's bigger than what you would need, so you'll certainly be within that bound of the margin of error. And then lastly, that note at the bottom, just like with desired sample size calculations for a single proportion, you have to round up no matter what, even if what's after the decimal point is something where you would conventionally round down. And it's for the exact same reason. If you round down, you're going to end up with a margin of error that's slightly too big. For this example, I think the best place to start might actually be the third bullet point, because that's telling us what we're supposed to be going after. We want the margin of error to be no more than 2 miles per hour with 95% confidence. So there are 2 things that we need. The other thing that we need is an estimate for the standard deviation. That's in the second bullet point. So is some other stuff, but really the only thing that we need is that 8. And those are the only things that we need, the things that are in blue toward the bottom of the screen. In that second bullet point, the 25 and the 11.6, you would certainly have them if you had that sample data, but you don't need them to compute a desired sample size. That formula doesn't have an X bar in it, and it doesn't have another N in it somewhere. The only thing you need is that 8. Substituting in and simplifying, if we substitute in those 3 values, we end up with N being 61.47 rounded to 2 places, but we have to round up to the next integer, so rounding up to 62, that would be the final answer. If we have 2 sample size examples, you can anticipate that the other one would be one where we don't have an estimate for the standard deviation that we can use. That would be correct. Like it says there, suppose we want to estimate the average GPA at a college with a margin of error of 0.1 with 99% confidence. There's the bound in the margin of error, the 0.1. 99% confidence implies that Z star has to be 2.576. And the other thing that we need is an estimate for the standard deviation. We don't have a previous study to work with, so this is where we have to set sigma tilde equal to the range divided by 4. And this is a scenario where we can figure the range out. The lowest possible GPA is 0, and the highest possible GPA is 4. So the range would be 4 minus 0, which is 4. Therefore, sigma tilde, if that's the range divided by 4, that's going to be 4 divided by 4, so it's 1. Substituting in and simplifying, we get that n is 663.58, and then we just have to round that up to 664. Hypothesis testing. To find the p-value, we can use an approximation of the sampling distribution of x bar, assuming that the null hypothesis is true. What was on the previous slide isn't anything brand new because it's what we did in Chapter 4. With Chapter 4, we generated a randomization distribution based off of the original sample and then centered at the value in the null hypothesis, and then we could get the p-value from there, using x bar as the cutoff. Now, in Chapter 6, we're still going to use an approximation of the sampling distribution, but we're going to use the central limit theorem instead of simulation, just like what we did with a single proportion. So if we assume that the null hypothesis is true, where mu0 is just whatever number is in the null hypothesis. So if the null was that mu equals 15, then mu0 is 15, that kind of thing. So if we're assuming that the null hypothesis is true, the mean of the sampling distribution would be mu0, whatever that number is, and the standard error would be sigma over the square root of n, but we're going to have to use s as a point estimate for sigma, so we're going to be computing it as s over the square root of n. Then, if n is at least 30, or if n is less than 30, but the histogram of the sample suggests that the population is normal, then you can compute the p-value using a t-distribution. This is really a two-step statement here, where we're basically saying if n's at least 30, you could apply the central limit theorem, so the sampling distribution should be approximately normal, but because we have to use s as a point estimate for sigma again, we're going to have to use the t-distribution again, just like we did with confidence intervals. So you end up computing a p-value in a test for a single mean using a t-distribution. And there's the test statistic at the bottom. That works the same way that it does for a single proportion in a general sense, if you think of it as point estimate minus mean of sampling distribution divided by standard error. It's still that same general format. This one's a little bit simpler because what's underneath the root is a lot less complicated than what you have for a single proportion. For the FICO credit scores example, the sample standard deviation was 89.946 and the sample size was 20, so we can apply the central limit theorem, but a histogram of that looks symmetric with a single peak in the center and no outliers. So we're okay as far as using this methodology goes. The test statistic would be 712.5, which is x bar, minus the value in the null hypothesis, the 695, and then divided by s over the square root of n. You end up with 0.8701 to 4 places. There are the two approximations of the sampling distribution. Again, the main point of these pictures is just that the one on the right looks like a smoothed out version of the one on the left. That's intuitively what that looks like, and that's the entire point there. So we should get similar p-values using either of those things. Here's the p-value that we get using a t-distribution with 19 degrees of freedom. Our test statistic was 0.8701. StatQ will only accept it to 3 places, which is why I have the cutoff as 0.870. And it looks like we're getting a p-value that's a little bit bigger because we have 0.198 in each tail, whereas with the randomization distribution we had 0.185. And so yeah, there is a difference between what we're getting here and what we would have gotten in Chapter 4, but it's nothing that's too crazy. You still end up with the same conclusion. For this example, that first bullet point says the average farm size in the U.S. is 444 acres. And we want to see if the average farm size in Oregon is lower than the national average. Going down to the hypotheses, those you can put together based off of that first bullet point. Lower than the national average, if mu is the average farm size in Oregon, we're looking for evidence that mu is less than 444. So that's our alternative. Then the null should be that mu equals 444. The second bullet point, we have our sample data, 40 farms, so n equals 40, and then we have x bar and s in there, 430 and 48 respectively. So since n is at least 30, we can apply the central limit theorem so we don't have to worry about looking at a histogram of the sample here. Under the assumption that the null hypothesis is true, what do we know about the sampling distribution of x bar? First, since the sample size is large enough to apply the central limit theorem, the sampling distribution should be approximately normal. However, since we have to use s as a point estimate for sigma, we're going to have to use a t-distribution to compute the p-value, more specifically a t-distribution with 39 degrees of freedom, since n is 40, and the degrees of freedom should be n minus 1, so we end up with 39. The mean will be 444. There's the part that comes from the assumption that the null hypothesis is true. And then the standard error, s over the square root of n, works out to be 7.5895 to 4 places. Finding the test statistic and the p-value, There's the test statistic. We take the 430 x bar and standardize it, subtract the mean of the sampling distribution, and then divide by the standard error. You end up with negative 1.8447 to 4 places if you don't round any intermediate steps off. Then for the p-value, there was a less than in the alternative hypothesis, so the p-value should be a left tail. The degrees of freedom is 39, which is what we said that had to be. And that left tail needs to be bounded at the test statistic. And again, StatKey will only accept that value to 3 places, so I have it as negative 1.845, and we get a p-value of 0.036. As far as the decision about the null hypothesis is concerned, alpha was 0.05, p-value is 0.036, so the p-value is less than alpha, so we should reject the null. Then the full-fledged conclusion, there is sufficient evidence to conclude what's in the alternative hypothesis, that the average farm size in Oregon is lower than the national.